All right, everyone, this is a continuation of the review for the Calculus 1 final exam. Problem number 7 was y is equal to sine of the quantity 7x to the fourth plus 6x plus 4. And here we're going to use the chain rule to find its derivative. All right, so in this case here, we want to find out what dy dx will be. So dy dx is the derivative of the sine is going to be the cosine of that argument, 7x to the fourth plus 6x plus 4, or I should say the angle, and that's going to be multiplied by what's inside using the chain rule. The derivative of 7x to the fourth would be 28x to the third, plus the derivative of 6x would just be 6. And if you want to, you can pull that 28x to the third plus 6 in front of 7x to the fourth plus 6x plus 4. And that would be your derivative for y equals sine of the argument or the angle 7x to the fourth plus 6x plus 4. Okay. All right, problem number, it's not problem number 9, this is problem number 10. I'm sorry. So that's problem number 10. All right, problem number 11 is this. Use implicit differentiation to find the derivative of 7x to the fifth plus 5y to the fifth equaling to 12xy. Okay. So number 11, we're using implicit differentiation here. In this case, every time we take the derivative of y, we have to include dy dx in it. So for 7x to the fifth, that derivative would just simply be 35x to the fourth, and then plus the derivative of 5y to the fifth, bring the 5 down, multiplied by that 5 in front, it'll be 25y to the fourth, but we must include dy dx. And then that's equal to that 12xy. We have to use the product rule on that one to take its derivative. So in this case here, I'm going to treat the first as 12x and then the y by itself. So here, this will be the first, that's going to be 12x, times the derivative of y, that would be 1, but we must include dy dx. I left something off. The first is 12x. Then the derivative of y would be dy dx, plus the second, which is your y, times the derivative of 12x. That's just going to be 12, and I'm going to put the 12 in front of that y. Now I'm going to collect all the terms that have dy dx on the left side, and all the other terms will go on the right side. So I got the 25y to the fourth dy dx. But if I move that 12x dy dx over to the opposite side, it will be a minus 12x dy dx. And that's equal to, and then 12y is already on the right side. The 35x to the fourth, I will move that over to the other side. It will be minus 35x to the fourth. Now on the left side, I can factor out the dy dx. If I factor that out, that would be 25y to the fourth minus 12x. That's equal to 12y minus 35x to the fourth. Now, to get dy dx by itself, I'll divide both sides by 25y to the fourth minus 12x. So that means dy dx will be equal to just that, 12y minus 35x to the fourth, all divided by 25y to the fourth minus 12x. So that's how we take the derivative of that equation using implicit differentiation. All right, number 12. We're going to find the derivative of this logarithmic function. The derivative with respect to x of the natural logarithm of 5x plus 2 divided by 5x minus 2. Okay, and that's this right here. So now, all we need to do here is start with the derivative of the natural log of this argument here. That's going to be 1 over that 5x plus 2 divided by 5x minus 2 times the derivative of this argument on the inside. Here we have to use the quotient rule for that. So here, I'll do the bottom, which is 5x minus 2, times the derivative of the top. The derivative of 5x plus 2 ends up being 5, minus the top, which is 5x plus 2, times the derivative of our denominator, which is 5. All that's divided by the square of that denominator, 5x minus 2, quantity square. Now, the reciprocal of this, we're going to flip that over. So that 1 over 5x plus 2 divided by 5x minus 2, the 5x minus 2 will be on top, and 5x plus 2 goes on the bottom. This we need to simplify using distributive property. So here I'm going to have 5 times 5x, that's 25, x squared, minus 2 times 5, that's 10. I'm also going to distribute the minus with the 5 over the 5x plus 2. Well, 5 times 5x is 25x, but the minus sign makes that minus 25x. Okay, and I need to make a correction here. This is just plain 25x. 5 times 5x is 25x. And then 5 times the 2 will be 10, but that minus sign makes it minus 10. Over 5x minus 2, quantity square. So that means here, these 25x's are gone. Also, I'm going to divide out this 5x minus 2 with one of the 5x minus 2's here. So I have 5x minus 2 in the denominator. Then when I simplify this, minus 10 and a minus 10 would be minus 20, divided by that 5x plus 2, multiplied by 5x minus 2 in the denominator. And this is actually what the derivative with respect to x of the natural logarithm of 5x plus 2 divided by 5x minus 2 would be. Negative 20 divided by 5x plus 2 times 5x minus 2. And I would leave it like this. All right, so that's problem number 12. All right, number 13 looks like this. Here you're finding the derivative of the inverse trigonometric function. Y is equal to the inverse sine of 4x to the 5th. Okay. And you do need to be familiar with the derivative of your inverse trig functions here, like the derivative of the inverse sine of x. This will give you, that means that dy dx will be this, 1 divided by the square root of 1 minus x squared. That's just something you need to be familiar with here. So if I do dy dx, is this. is going to be 1 over the square root of what's inside the parentheses. Well, actually 1 minus what's inside the parentheses, 4x minus 5. That's going to be squared. Times its derivative. The derivative of 4x to the 5th would be 20x to the 4th. Okay? I also gave rules when your u is a differentiable function, and here u is a differentiable function, so you have to apply the chain rule here. Because the derivative of the inverse sine would be this, and that 4x to the 5th will have to be squared. Then you have to take your inside derivative, which is 20x to the 4th. So here, I'm going to have 20x to the 4th in the numerator divided by the square root of 1 minus, if I square the 4, that's 16. X to the 5th would be squared. If you're raising a power to a power, you multiply the exponent, so it'll be x to the 10th. So this is my final answer for the derivative of the inverse sine of 4x to the 5th. 20x to the 4th divided by the square root of 1 minus 16, x to the 10th. Okay. All right, now problem number 14. A spherical balloon is inflating with helium at a rate of 72 pi cubic feet per minute. How fast is the balloon's radius increasing at the instant the radius is 3 feet? So in this case, we are told what dV dt is, because 72 cubic feet per minute will have to be the rate that the volume of that volume. So dV dt is 72 pi cubic feet per minute. We're trying to find dr dt. How fast is the balloon's radius increasing? At the instant, the radius is 3 feet, so your radius there is 3 feet. That's given to you. There is a formula for the volume of a radius. The volume of a sphere, since we're dealing with a spherical balloon. So here the volume there is going to be 4/3 pi r cubed. Let me make that 4/3 look like a 4/3. 4/3 pi r cubed. Now what we need to do here is take the derivative of each term with respect to time. So the derivative of v would be dv dt. And then 4/3 pi is a constant. The derivative of r cubed with respect to time would be 3r squared dr dt. So that means dv dt is equal to, and in this case here, those 3's divide out. I will have 4 pi r dr dt. So now in this case here, let's do our substitution here. dV dt is given to you as 72 pi cubic feet per minute. So I just replace that with 72 pi is equaling to 4 pi, and this should be r squared. Because r is 3 feet, so that'll be 3 squared times dr dt. Okay. That looks a little bunched up, so square 3r dr dt. All right, now we got 72 pi is equal to 3 squared is 9 times the 4 in front would be 36, so I have 36 pi dr dt. And to get dr dt by itself, I'll divide both sides by 36 pi. So here dr dt is equal to 72 divided by 36 will be 2. And this will be in feet per minute. So that means that the radius is increasing at a rate of 3 feet per minute. Okay, 3 feet per minute. All right, now problem number 15. This one has like 10 steps to it, so this might take a while, so bear with me. You're given the function f of x equals x cubed minus 6x squared plus 9x, and you're going to answer the following. Part A, you're going to first find the derivative, then find the second derivative, identify your critical points, identify the inflection points, and then on what intervals are the function increasing, on what intervals are the function decreasing, and what intervals are the function concave up, on which intervals are the functions concave down, identify your local maxima and local minima. 10 parts to this problem. And our function is f of x is equal to x cubed minus 6x squared plus 9x. And in this case here, we start by finding the first derivative. That means f prime of x. For x cubed minus 6x plus 9x, 6x squared plus 9x, its derivative will be 3x squared minus 6x plus 9. That's your first derivative. That's part A. Part B is the second derivative, f double prime of x. We take the derivative of the first derivative. For 3x squared minus 6x plus 9, its second derivative would be 6x minus, now I made a mistake. Bring the 2 down, multiply by 6, it'll be 12. So this should be 12x plus 9. And then the derivative of minus 12 would be minus 12x would be minus 12. Does everyone see what I'm doing here? This 3x squared, derivative of minus 6x squared, that'll be minus 12x and then plus 9. That's your first derivative. Second derivative will be this times the 3 will be 6x minus 12. Okay, so that's part B. Part C is identify your critical points. To find out what your critical points are going to be, we let f prime of x equal to 0. So that means I have 3x squared minus 12x plus 9 equal to 0. And in this case here, what I'm going to try to do is factor out the 3, since there's a common factor there. So I have x squared minus 4x plus 3 equaling to 0. And I can factor x squared minus 4x plus 3 into two binomials here. That x squared breaks up as x and x. Factors of 3 that gives me minus 4x will have to be minus 3 and a minus 1. So I have 3 times the quantity x minus 3 times x minus 1 equal to 0. Then we set each factor equal to 0 and solve for x. So I have 3 equal to 0, x minus 3 is equal to 0, x minus 1 equal to 0. Well, that 3 equals 0 is a false statement, so we can eliminate that. For the x minus 3 equal to 0, that means x must be equal to 3. And for x minus 1 equals 0 must mean x equals 1. So these are my two critical points, x equal 3 and x is equal to 1. Now, part D are your possible inflection points. We take our second derivative, which is 6x minus 12. We take that second derivative, set that equal to 0. And my second derivative is 6x minus 12. That's equal to 0. Move the 12 over to the other side. It'll be 6x equals 12. That means x is equal to 2. So my possible inflection points will be at x equals 2. Now, on which intervals is the function increasing? Well, this is where we put all of this on the table. So here's E. Now my critical points are at x equals 3 and x equals 1, if you recall. Okay, so here I'm going to put, let's see, 1 goes here, and 3 will go here. I have three different intervals. One from negative infinity up to 1. The other one is from 1 to 3. The other one is from 3 to infinity. Now here we're going to pick test values here for each one of these intervals. So from negative infinity to 1, my good test value will be x equals 0. And I'm using the first derivative, which is that 3x squared minus 12x plus 9. Substitute 0 in that f prime of x function. So here, f prime of 0, f prime of 0 is this, 3 times 0, and that's squared, minus 12 times 0 plus 9. This will be 0, that's going to be 0 plus 9, which will be 9. It is positive, so that means if it's positive on that interval, the function will be increasing. Okay, is that 1C? Well, if you have questions, email me. And now for x equals from 1 to 3, let's take a test value of 2. So that means f of 2 would be this, 3 times 2 squared minus 12 times 0 plus 9. And I'm going to go ahead and use my calculator for this. 3 times 2 squared minus 12 times 2. Oh, and this should be a 2 right here. Should be a 2 right here, and then plus 9. You'll get negative 3, and that's negative. So that means between 1 and 3, the graph of that function would be decreasing. It's decreasing on the interval from negative 1 to 3. And then from 3 to infinity, I will use x equals 4. And just replace the x with 4 in that original function. I mean, not the original function, f prime, the first derivative function. So it'd be 3 times 4 squared minus 12 times x, which is 4, plus 9. Let's see, 3 times 4 squared minus 12 times 4 plus 9. And I get positive 9. And it is positive, as I mentioned. So that means from 3 to infinity, the graph will be increasing. So we pretty much answered E and F. For E, the function is increasing on 2 intervals. From negative infinity to 1, and from 3 to infinity. And for part F, where the intervals on which the function is decreasing, well, it's decreasing only on one interval, from 1 to 3. Okay. Now, part G, we want to know the intervals in which the graph is concave up. So we're looking for concavity in this case. Our possible inflection point is at x equals 2. So I'm going to put 2 right here. And my interval is from negative infinity to 2, and then from 2 to infinity. And I'm using the second derivative function, f double prime of x equaling to 6x minus 12, and substituting them in my test values, with my test values here. So from negative infinity up to 2, I'm using x equals 0. So f double prime of x, or f double prime of 0, I should say, would be 6 times 0 minus 12. Ends up being negative 12. So that's negative, meaning that the graph of that function would be concave down. And then from 2 to infinity, I'll use x equals 3. And then f double prime of 3 would be 6 times 3 minus 12. Well, that's 18 minus 12, that's 6, which is positive. So that means from 2 to infinity, the graph of the function would be concave up. So in part G, the graph is, the function will be concave up. On this interval from 2 to infinity, and then concave down for part H. From negative infinity to 2. So that's given to us in that problem. Now they want the local maxima and the local minima. Well, look at the table in part E. Notice we're increasing at 1, and after 1 it starts to decrease. So that's a local maximum. And then at 3, to the left of it, we're decreasing, and then to the right of it, we change to increasing. So that's your local minima, or minimum. So for part I, your local maximum, there's only one, will be at, in this case, at x equals 1. And then your local minimum, which is part J, will be at x is equal to, you can see, it's going to be at 3. Okay. All right. There will be another part to this video, so be on the lookout for this as well, while I'll finish the remainder of the review sheet for the final exam.